Chapter 3, solving systems of equations and systems of inequalities as well. Section 3.1 reintroduces to you two of the ways that you can solve systems of equations. There are four. You can solve by using tables, you can solve by graphing, you can solve algebraically, you can solve using matrices. And of those four, solving algebraically, you can solve using substitution, you can solve using elimination. So there are lots of ways to solve systems of equations. You're going to learn all of them in this chapter. You've learned the vast majority of them already in Algebra 1. So a lot of this chapter is going to be review for you, at least the first couple sections are, hopefully. So keep that in mind. Section 1, solving systems using tables and graphs. So right away we're getting into solving systems of equations, but we're looking at just tables and graphs. So the real question here is, why do we want to solve a system of equations? What does it look like to us? Okay? Get into that in a second. Let's look at the vocab first. We have system of equations. It's a set of two or more equations involving the same variables. In Algebra 1, you guys had something like maybe 3x minus 2y equals 5, and then 2x plus y equals 7, or something like that. And then you'd have to solve that system using whatever method it was that they told you to use. Elimination, substitution, graphing, using a table, whatever. Well, that was Algebra 1. In Algebra 2, we can have a third variable, or we can have as many variables as we want. So over here I could have like a 4z plus 3x and a 2z minus 2x. And then I could have a whole other equation. 6z plus x equals 8. So now it's a system of three equations with three variables, and we'd have to solve that. We're going to have three answers. A linear system is a system involving linear equations. On your Chapter 2 test, some of you gave me graphs that were not linear when I was giving you an equation that should have been a line when you graphed it. You got to pay attention. Linear equations are a linear system. They graph lines. Solution of a system is a set of values, for example, an ordered pair in Algebra 1, or this new term here, an ordered triple, that makes each equation in the system true at the same time. So on a graph, what does that look like? What does a solution to a system of equations look like on a graph if I have a linear system? On a graph, if I have a linear equation, what does it look like? It looks like a line, right? So if I just kind of sketch a graph in here, and I draw in a nice purple line, so I have some equation, it graphs that line. What does that line represent? No. We're not talking about scatter plots here. We're just talking about an equation that I gave you. This is its graph. What does it represent? But what part of that equation? The solutions to the equation. That's right. So if I give you some equation, like maybe this equation is y equals negative x plus 4, I don't know. The graph represents visually for us all of the ordered pairs that make this equation true. Every ordered pair that makes the equation true is on this line. That's the whole point of graphing. The graph just shows us visually what ordered pairs work for that equation. These ordered pairs here, they don't work for this equation. They'll give you a false statement. But every ordered pair on this line gives me a true statement here. And that's why we graph, so that we can visually see what's going on. Okay? You got to remember that. That's like Algebra 1 stuff right there. Well, now what I'm going to do is I'm going to give you a second equation. It's going to be a linear equation. It doesn't have to be, but just to start off for this example, it will be. Maybe y equals 2x minus 5 will be my second equation. Now when I graph that second equation, that graph will represent all of the ordered pairs that make that equation true. So the negative 5 would be down here, and then I have a slope of 2. So maybe that is my graph for my red equation. Okay? So what I have here is a visual representation of all of the ordered pairs that make this equation true. None of these ordered pairs work for that red equation. None of these ordered pairs work for that red equation. So let me ask you one more time. What does the solution of a system of equations look like? It's where they intersect. That's right. So let me pick a cool color, raspberry. There. Where the two lines cross. So in words, what does this point right here represent? What is that? It's the ordered pair that works for both equations only. It's the only one that does for lines. You're going to have one point right here, one ordered pair that works for both of these equations. And that's why we call them a system of equations. When you graph them, you will wind up with an intersection. And that intersection is the one ordered pair that works for both equations. Okay, so on a graph, what does the solution of a system look like? Yeah, they look like intersection points. So one method that we have for solving systems is by making tables and graphs. And we're going to start with tables. Pretty quickly, though, we're going to move to graphs because tables get the job done, but they get the job done kind of poorly. It's kind of a very primitive way of solving systems of equations. Oh, well, I guess we're going into graphing right away, so never mind. Did I skip something? To solve a system by graphing, you have 3 steps. First of all, put each equation in slope-intercept form, so you're going to see y equals form. Choose an appropriate scale for the graph. With experience, you'll figure that out, but you might have to go by 2s or something like that, okay? It's not like scatter plots where everything's got to take up the entire grid. You just got to have the intersection on the graph. So carefully graph each equation. And there's the word carefully again. I've been saying that all year long. When you graph in this class, you have to be extremely careful. If you are not extremely careful, you will find the wrong solution. Make sure the intersection shows on the graph itself. That means on the grid. If it doesn't, then the graph needs to be rescaled. So if I were to draw, just for example, a line like this and then a second line up here, this doesn't cut it. I got to be on the grid, so I'll have to rescale that. So let me go ahead and solve this first system by graphing. The first thing we need to do, according to my little steps that are sitting up here, is put these in slope-intercept form, which they're not. So I'll take this first equation here, and I'll use blue. I'm going to add 3x to both sides, and that gives me 2y equals positive 3x plus 8. And then I'm going to divide both sides by 2 to get y by itself, and that gives me y equals 3/2 x plus 4. Now I can graph that because it's in slope-intercept form. So I go to plus 4, 1, 2, 3, 4 right here. By the way, if you are still not sure about graphing, you need to get help and you need to figure out graphing because there's a lot of graphing in this chapter and you need to be good at it, like last week. Slope of 3/2, so up 1, 2, 3 over 2. Can't go any farther that way, so I reverse it, down 3, left 2, down 3, left 2. Down 3, left 2. Get as many dots in there as you can. Then I can draw that line in. Hopefully my scale won't need to be adjusted so that I have to go through and erase everything. We'll see. Very carefully, very accurately draw in that line. Then we move on to the second equation. I'm changing to red. I need to get y by itself here. You will need rulers every day in this chapter. Subtracting x from both sides gives me 2y equals negative x minus 8. Divide both sides by 2 and I get y equals negative 1/2 x minus 4. That's in slope-intercept form, so now I can graph that one. We go to negative 4 on the y-axis, which is right there. And then we have a slope of negative 1/2. So I go down 1, right 2. Down 1, right 2. Down 1, right 2. I'm out of room, so I reverse it. Up 1, left 2. Up 1, left 2. And look, when I put that dot down, I notice that I put a dot there on my previous equation. So I already know that that's my intersection point. Up 1, left 2, and I'm out of room. So now I can draw that one in, and I already know my intersection, which is nice. Very carefully draw in that line. You can see I need to recalibrate my board. So there's the graph. Now to answer the question, I have to tell what the ordered pair is. The graph itself is not enough. You have to include the answer as an ordered pair, otherwise you are wrong, because I need to know that you understand what you're doing. So you'll write the ordered pair where the two lines cross, and that would be negative 1, 2, 3, 4, so negative 4, comma, negative 2. There's your solution. So just to prove to you that what I'm doing is actually giving me the solution to both of these equations, we're going to take negative 4, negative 2, and plug it in. So I plug negative 4 in for x here, and I get positive 12. I plug negative 2 in here, and I get negative 4. Positive 12 plus negative 4 does give me 8. So that ordered pair is the solution for that equation. Do the same thing for the second equation. This gives me negative 4. 2 times negative 2 is negative 4. So negative 4 plus negative 4 does give me negative 8. So that ordered pair does work for the other equation as well, which means that this ordered pair works for both equations. So now I know for certain that that is my answer. That's how you check these problems. So for my next problem, what do I need to do first? Slope-intercept form. So I'll take the top one first. What do I do? Move the x over. So now I have negative 2y equals negative x plus 4. Now what? Divide by negative 2, so that gives me positive y equals positive 1/2 x minus 2. If you can't do that in your head, then write down all those steps. There's no shame in that. So now I'm ready to graph it. How do I graph it? Go down 2, good. Then what? So up 1 over 2, to the right, over and over. Reverse it, down 1, left 2, over and over. Until you're out of room, and then draw on the line. And I'm going to draw on that line very sloppily, right? Okay, what's next? Slope-intercept form. This one is very easy to do. We just subtract 3x from both sides, and we get y equals negative 3x plus 5. Now what? Okay, so we have positive 5, which is right there, and then a slope of negative 3, which means negative 3 over 1. So I go down 3, 1, 2, 3, right 1. Down 3, right 1. And then notice that we landed right on a dot that we'd already put down. So now we know exactly what that solution is. But we still need to finish off the problem correctly. So now we draw in that line very carefully. Practice drawing careful lines. You'll see why in a couple sections. So there's the graph. Am I done? Okay, so we got to write down the ordered pair to have our solution. What is our ordered pair? 2, negative 1. And then you would check it by substituting those values into both equations. Here's your steps for solving a system using tables. First of all, write each equation in slope-intercept form again. So again, that's going to be y equals some stuff. Then set up an x, y1, y2 table and choose some easy values for x. I'll show you what that means here in a second. Then solve each equation for each x value, paying attention to the relationship between y1 and y2. So I'm going to ask a question here. Are the values getting closer together? As I plug in x values, are my y values becoming closer together, or are they getting farther apart? If they're getting closer together, then I'm checking x values going in the correct direction. If not, then I need to reverse my direction and go the other way. So then you're going to keep going until an x value is found where your y1 and y2s are equal to each other. At that point, you'll have your ordered pair, the x value that you plugged in and the y values that you got. So solve by using a table. I'm going to write each equation in slope-intercept form. So again, I add 3x to both sides, and then I'll divide both sides by 2, and I get y equals 3 halves x plus 4. My second equation, I solve for y, subtracting x from both sides and then dividing both sides by 2, and I get y equals negative 1/2 x minus 4. Right? So now that I'm in slope-intercept form for both equations, I set up my x, y1, y2 table. I have x, I have y1, I have y2. And I'm just going to start picking some easy values for x. I have no idea where to start. So I'm just going to start with 0, 1, and 2, and we'll see if we're getting closer. If the y1 and y2 values are getting closer together, then we're going in the right direction. If they're getting farther apart, then we're going the wrong way. Okay? So I take 0 for x and I plug it in over here, and that gives me 0 here plus 4, which is 4. So I'm calling this one my y1 and I'm calling this one my y2. It just is notation that says equation 1 and equation 2. I take 0 and I plug it into my second equation, and I get 0 here minus 4, which is negative 4. So I did not get the same value for y1 and y2, so that means I did not find my solution yet, so I keep going. I take 1 and plug it in. 3 halves times 1 is 3 halves. 3 halves plus 4 is what? What? No. No. 3 halves plus 4. 3 halves is 1.5. So plus 4 would be 5.5. Right? You do? So 5.5. I'll just call it 5.5. I take 1 and plug it in here. Negative 1/2 times 1 is negative 1/2. Minus 4 would be negative 4.5. Are my values getting closer together or farther apart? They're getting farther apart. So am I going the correct way? No, I'm not. So instead of doing 2, I'm going to go to negative 1. Because I need to reverse directions so that I can get over to where my intersection point is. So now I take negative 1 and I plug it in. Well, 3 halves times negative 1 would be negative 3 halves. That's negative 1.5. Plus 4 gives me what? Negative 1.5 plus 4 would be positive 2.5. Take the negative 1 and plug it in over here. Negative 1 times negative 1/2 gives me positive 1/2. Positive 1/2 minus 4. Negative 3.5. Make your brain do these problems. Do this math. You will get stronger. Am I getting closer now? I was a difference of 8 units here. Here I'm only a difference of like 6 units. So I am getting closer. So I'm going the right way. So let's plug -2 in. Maybe we'll get the right answer now. -2 times 3/2 would be -3. -3 plus 4 is +1. -2 into my second equation now times -1/2 gives me +1. +1 minus 4 is -3. Did I get my answer now? Nope. Am I getting closer? Yep. So try -3. -3 here gives me -9/2. -9/2 is like -4.5. -4.5 plus 4 gives me -1/2. -3 times -1/2 gives me +3/2. +3/2 minus 4 gives me so +3/2 is +1.5. 1.5 minus 4, same as 4 minus 1.5. -2.5. I'm getting real close now. I'm hoping that maybe 4 will be my answer. So I'm going to stick 4 down there. I take -4 and plug it in, and I get -12/2, which is -6. -6 plus 4 is -2. I take -4 and plug it in here. That gives me -1/2 times -4, which is +2. +2 minus 4 is -2. Did I find my answer? That's the answer. So the x-coordinate that I picked was -4, and the y-coordinate that I got once I plugged -4 in was -2. Close the parentheses. There's your answer. -4, -2. Which way is better? Graphing or tables? Graphing, for sure. Okay? But this is how you can do this using tables. Now I want to point something out to you. We got an answer of -4, -2. This system right here is the exact same system that we started off with right here. Same exact system, same exact answer. Graphically, there it is. Using a table, that's what you got to go through to get there, especially if you start in the wrong spot. Okay? This is a very primitive method. It takes forever sometimes. But sometimes this is the only way you can do something like this. So you got to know how to do it. All right, next. That one's for you. Go ahead. Oh, this is the one you were doing? All right. Well, now you can do this one. So for the second problem, again, we put this in slope-intercept form. For the first equation, we get y equals what? And for the second equation, we get what? These look familiar? Yeah, it's the second graphing one that we did. So we already know what the solution is. The idea is, though, that you understand how you set this up. y1, y2. I'll call this one y1, the top one, and the bottom one y2. So here's our table. I'll just go 0, 1, 2. Plug in 0 and you get -2 for y1, you get +5 for y2. Plug in 1 and you get 1/2 minus 2, which is -1 and 1/2. You get +2 here. So the question is, are we going the right way? Yeah, the difference between y1 and y2 is shrinking. So that means we are going the correct direction. I take 2 and I plug it in. 1/2 times 2 is 1. 1 minus 2 is -1. Take 2, plug it into the second equation. -3 times 2 is -6. Plus 5 is -1. I got the same value right there. So that means I have my ordered pair. It is 2, the x value that I plugged in, comma, -1, the y value that I got for both equations. Okay? So I quickly stumbled across the answer on that one. I kind of used our answer, though, from the previous problem to help me. So, but that's the idea. That's right. Okay. The table shows the populations of New York City and Los Angeles from census reports from 1950 to 2000. Assuming these trends continue, when will the populations of these regions be equal, and what will that population be? So if you look at New York City from 1950 to 2000, what can we say about the population of New York City? It's growing. If you look at Los Angeles from 1950 to 2000, what can we say about the population of Los Angeles? But it's growing too, right? Right? Aren't they both growing? Yeah. But if you look, it's going from like almost 13 to 14.7 to 16.1 to 16.1 to 18 to 21. This is not growing as fast as this one is. Okay? So that's like a shallow line and a steep line. These guys will cross. The question is, where do they cross? And when do they cross, and what is that value? So the nice thing is here, we're going to have to develop equations for both of these. And then we'll have to graph them using an appropriate scale. And then, once we've done that, figure out where that intersection point is exactly, because we need to graph very accurately. How's that sound? Pretty fun? No. Or we can use our calculators. So bring up your calculator and enter all of this data into a spreadsheet. And then graph it on a data and statistics plot. So what I've done is I've created a spreadsheet, and I'm calling the first column year, and then I'm calling the second column New York, and I'm calling the third column Los Angeles. Now I'm not going to enter in 1950, 1960, and so on. I'm going to use my usual pattern. I can go 0 and then by tens. So 0 will be 1950, 10 will be 1960, and so on. Then I go back up, and I don't have a choice here. I have to enter in all those numbers. So that'll take forever, but that's what we got to do. So now I've entered all those numbers in, and again, make sure you hit enter on that last cell, otherwise you'll get an error when you try to do what we're about to do. So I'm going back to the home screen, over to data and statistics. Tell the thing what to do. So go down to the x-axis, and we want to call that, let's see, I called it year. Uh-oh, hopefully I didn't screw up. And then over here, I want Los Angeles. So now I'm going to enter a trend line in for Los Angeles. So I want to analyze and regression and show that linear trend line. Now I'm going to write that down. 251,030x plus, and then we have some scientific notation there. So that equation was y equals 251,030x, and then the 3.815 blah 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 E6 is scientific notation. That's plus 3,815,140. Okay. All that means is I move the decimal place 6 places to the right when I see that E6. That's how a calculator represents scientific notation. It's the same as 3.815 times 10 to the 6th. So I move the decimal places over 6 places to the right, and now I have my answer. That's for which city? That was Los Angeles. So now what I'm going to do is go back to my calculator, and on the same graph, since that's Los Angeles, I'm just going to click on the y-axis again and switch to New York. it's going to understand what I am telling it to do here when I do that. So I click on New York, and now the label over here is New York. The data has changed, the trend line has changed, and the equation has changed. I didn't have to come up with a brand new equation. I can just change the variables on this one graph and get my new equation. So now I write that one down. It is 146,758x plus, and now we have 1.28741 E7. That means times 10 to the 7th power. So I got to move the decimal place over 7 places to the right. 1, 2, 3, 4, 5. So I'm going to have to add 2 zeros to the end. So I come back to my notes here and I write down the equation. Y equals 146,758x plus 128,741,00. That's LA. The second one is New York. So now what we need to do is graph these two equations, and we're going to do that on the calculator. Type these two equations in on the calculator, zoom out. You'll have to zoom out quite a ways until you see where they intersect. Where they intersect is the answer. So to do that, go back to the home screen and go over to Add Graph to your document. Now you have a graph. And then you can type in those two equations that you just came up with. So we have the 251,030x plus 381, so 251,030x plus 3815,140. Hit enter, and of course it's not going to show up on the graph because we've got to zoom out. Then you can enter the second one in there, zoom out, and you'll find your intersection point.